Hi everybody. In this video, we are going to take some examples on chapter 4 or on the part of synchronous machine. Actually, the first example here is on the calculation of the parameters of synchronous generator. So, based on the value that obtained from the test, either for open circuit test or short circuit test or the DC test here, we are going to calculate the parameters or the variables or the components of the equivalent circuit of the synchronous generator. So in this example here, we have 200 kVA synchronous motor, and this synchronous motor actually it has it is 480 volt, okay, and 50 hertz. This is for the value of F, and it's Y connected. Actually, we need to to consider is the generator is Y connected or delta connected. I mean star or delta, because this will affect the value of the voltage and of the current for both for the phase and for the line also. Okay, Y connected synchronous generator with a rated field current of 5 ampere. So this is the value of IF. So IF here equal to 5 ampere. It was tested under the following and the following data were obtained. So from the open circuit test, we have the VT open circuit, which is 400 or 540 volt. So this is open circuit test, means we are going to run the synchronous generator without any load. Okay, so then we are going to measure in this case the current will be zero, or the armature current will be zero, but we have a voltage on the terminal of the generator, which is 540 volt. Actually, this is the line, we call it the line voltage. It's not the phase. Since we have three phase, so we need this voltage is measured between the two, between line to line. It's not for the each phase. So later on, we'll see how to convert it from line to line into phase voltage. Then we have the short circuit or the load current here, or in the short circuit test is 300 ampere. Both are tested at the rated IF, so the field current is always is equal to 5 amperes. When a DC voltage of 10 volt, he said here a DC voltage, so we are going to talk about the DC test, which is used to calculate the value of the stator winding resistance, or in the case of synchronous machine, we call it the armature winding, okay, of 10 volt was applied on the two terminals. So we have the two terminal. The generator actually has three terminals because it's three phase, but this voltage was applied on the two terminals, and the obtained current was 25 amperes. So this current actually come from the DC test. Okay, we apply 10 volt, we got the current is 25, so it's easy for us to calculate the value of RA in this case, because we have the voltage, we have the current, we can apply the Ohm's law, but we need to consider the connection. Is it delta or star? Okay, the question here, find the generator model. You want to draw the equivalent circuit of the generator and highlight the value of the parameters for the generator, like the armature resistance, armature voltage or internal voltage of the generator, and also the value of the synchronous reactance. Okay, and here he said the armature resistance and the approximate synchronous reactance means XS. You want to find the armature resistance, which is the value of RA, and also the value of XS. Both need to be found in addition to the value of EA, because all these three variables or three parameters represent the rotor or the armature circuit of the synchronous generator. Okay, we can see here in the next and the solution here from the first test that we conduct, which is the DC test. The test is conducted by connecting a 10 volt DC to two terminal of the generator. Here we have two terminal here are connected, while the third terminal is there, it's open. No current will go through RA here in this part. This one no current, because this terminal is open, so the current will go through this line, through this winding RA1, then RA for the phase 2, and then it will return again to the voltage source. So this is how the current will go through the circuit. Okay, so 10 volt will go through the resistor RA and RA. Both RA are connected in series, because here it looks like it's disconnected here or cut. This part is not there, so it is RA plus RA, so we have 2 RA. So the 2 RA here give you the voltage based on Ohm law, which is VDC over IDC. So this is Ohm law. The value VDC over IDC equal to R2RA. Why 2RA? Because we have 2RA connected, RA and RA connected in series. So the value of RA here will be VDC over 2IDC. So we substitute for VDC, which is 10 volt, the IDC, which is 25. So the value of the RA, or the armature resistance, is 0.2 ohm. Okay, so this is the value of the first parameter of the synchronous generator equivalent circuit. Then the voltage that we got from the question here, he said EA equal to 5, or he said VT or V phase VT open circuit. If we go back, he said the value of the VT open circuit is 540. We said this is the voltage for line to line. It's not the phase voltage. So this V line to line we need to find for the phase. So in order to find the phase, we need to find V phase here, which equal to V line or V terminal over Z3. Okay. In the case of the star, connection here, the V line or the V phase equal to the V line over Z3. V phase equal to V line over Z3, and I phase, which is the I of the phase here, any the current go through the phase, is equal to I line. So this is for star connection. In the case of the delta connection, the situation will be V phase, and let me write it here. So for the case of the delta connection, so the V phase equal to V line, I phase equal to I line over Z3. Okay, so please take note, this one for delta and that one is for star. Okay, so here we have star connection, so the current is the same, but the voltage will be V phase equal to VL over Z3. So we have VL here, which is V terminal 540 over Z3. So this will be the value of the EA, or the internal voltage of the generator. Okay, so since we have the value of EA and we have the value of RA, now we just need to find the value of XS, okay, or the synchronous reactance. Okay, so the synchronous reactance here, or XS, is can be found because usually the value of Z, when we learn Z usually consists of two parts, R plus minus JX, correct? So if it's XL, so it will be plus. If it's XC, so it will be minus. So in the case of the synchronous generator here, the Z will equal to RA plus JXS. This is the value in rectangular form. If we want to find the magnitude of XS, so we are only going to talk about the value without the angle, so it will be ZS square minus RS square. Why? Because actually the formula said Z equal to RA plus JXS for the synchronous generator. So if I want to find the magnitude of Z, it will be RA square plus XS square. If I want to find XS, it will be ZS square minus RA, all under square root. Okay. Then we substitute the value for ZS here. How we can find the value of ZS from the circuit here, from the open circuit test? So it will be EA square over I short circuit. I mean, in order to find the synchronous reactance, we need to consider the value of, we already talked about this in the video about the test of the synchronous generator. So it will be EA square. This will be ZS square, ZS equal to EA over IA. So we have ZS square, so it will be EA square over IA square. This EA from open circuit, this one is from short circuit. Okay, so minus the value of RA already find here in this test for the DC test. So we just find 3118. This one come from this part, which is the value of EA. Then over 300, this one, the short circuit current is come from the, in the question here, he said that short circuit current is 300. So we just substitute for the 300 in this equation. All square minus 0.2 square. So you got the value of XS, which is 1.02 ohm. This is the exact value of synchronous reactance. In order to find the approximate value, we just divide the value of the EA. This is the formula to give you the approximate XS, which is EA from open circuit. This is from open circuit. This one from short circuit. So it is 311 over 3. So the difference a little bit. It's in the previous one it was 1.02. Here it is 1.04. So the approximate value. Then since we have XS, we have RA, we have EA, so just we need to draw the equivalent circuit here. So this is EA, which is 311.8 or 312, almost 312. RA is 0.2 from the DC test. XS is 1.2, so from the DC and I mean from the open circuit and short circuit test. So this will represent the value or the equivalent circuit. IF here will equal to 5 ampere at the rated or the full rated current. So this is how to find the parameters of the synchronous generator by using the uh, test, either RDC DC test or open circuit test or short circuit test. Now we will see another example here. So in the second example, we are going to see the impact of changing power factor on the parameters of the synchronous generator. Okay, so we will see how the power factor will affect the value of the voltage taken from the synchronous generator, and we are going to consider the three states of power factor, either lagging, leading, or equal to 1. So here the question said we have three-phase generator Y connected here. So it is Y connected. It has 6 poles, and synchronous generator has also the frequency is 60. The value of the terminal voltage here, which is VT here, equal to 480. Okay. The synchronous reactance, this is the value of XS. XS equal to 1 ohm. VT equal to 480, and we have F equal to 60 hertz. Okay, then we have each full load armature current, that means the full load I armature full load equal to 60 amps. Okay, then we have at the power factor 0.8 lagging. So in the first case, or in the normal condition, power factor equal to 0.8 lagging. Always when you find the power factor or you calculate the value of power factor or you use the power factor, you should know is it lagging, leading, or equal to 1. Okay, its friction and windage losses here. This is, we'll talk about the power loss. So as we already see the power flow from the input to the output of the generator, we have mechanical losses, we like windage losses and also friction loss. And also we have core losses here, which is 1 kilowatt, and all these are 60 hertz full load. When we say full load, that means we are talking about 60 ampere current. Okay, assume that the armature resistance and therefore I square R, armature resistance means RA. So he said assume RA equal to 0. Okay, if RA equal to 0, so the losses I square RA will be equal to 0. Here when he said ignore, so it will be equal to 0. The field current has been adjusted such that the no load terminal voltage is 480. So he talked about the field current here, or IF. Okay, he said IF is adjusted to get the value of the rated voltage or the terminal voltage in the case of no load. Okay, the question here, it consists from different parts. Actually, this type of question is need to focus when you solve it. So go step by step. So what is the speed of the rotation of the generator? When we talk about the speed, we say the generator, it has only one speed. Synchronous machine has only one speed, which is the synchronous or the machine speed, the same. So the ns here or nm can be calculated equal to the n of the generator. Nm is equal to ns is equal to 120 f over p, correct? So we have 120, we have the frequency is 60 and we have the number of pole is 6 poles. So we just substitute here, we can find the synchronous speed of our generator, and after we find the synchronous speed in rpm, we can convert it into or to find omega m here, or the angular speed, we by multiply by 2 pi over 60. So we can find the value of the synchronous generator either in rpm or in the radian per second. The second part, which will be, or the step b here, or the section b, is more it will be repetitive. So you are going to repeat the same steps for the three cases of power factor. Power factor is lagging 0.8, power factor is equal to 1, power factor is leading 0.8. So you are going to do for the first step, for example, then you are going to repeat again for the second power factor, for the third power factor, and it's more related to the phasor diagram of the synchronous generator that we already mentioned in the previous videos. Okay, so we'll see here how we can how we can calculate the values of the different power factors. So this is the first part. The main thing actually you need to know, if we have the voltage for the star connection, so you need to divide by over set3. If you set delta, no need, you just use it. V phase equal to V line or V terminal. But in the case of Y, you need to divide over set3. Okay, so we have the terminal voltage is 480 divided by set3, so this will be the phase voltage. So each phase has 277 volt. So we have three phase. We cannot say the summation of the three phase, no, because the three phase, each phase has a value of voltage and it has angle. So the difference angle between each phase to other phase will be 120. We say the first 0, the second will be 120, the third will be 240. So the difference between phase to phase is 120 degree. So it will be like this one. So if this is 0, this will be, if this one is phase 1 A, this will be phase B, this will be phase C. So this is when we talk about the three phase. So this 120 here 240, okay, and here it will be returned again to the 0. So 0, 120, 240, again 0. Okay, so it is 360 degree over 3. So this is how we can find the different phases. So each phase, it has 277 volt magnitude and it has angle of 120. Okay, at no load here, the armature current, actually IA, equal to 0. Why? Because when we said no load, that means we are going to run the armature, but without any load. So the terminal of the generator or of the armature or stator of the synchronous generator will not be connected to any resistive, capacitive, inductive loads. No loads. Okay. And the internal generated voltage here, EA, will be 277. It is the same as the V phase because there is no load, no voltage drop. So the output voltage is the same as the induced voltage. Okay. This is how to calculate the speed. We already mentioned for it before. So we said 120 FEB over, so substitute, we got it 1200. Then we have it in the radian, we multiply by 2 pi over 60. We got it the value in radian per second. Okay. The next part, which is AB here, we said B consists of three steps. The first step, we calculate for the power factor lagging power factor 0.8. The second for one power factor equal to 1. The third is for power factor leading 0.8. Okay. So we say the phasor diagram is the main to know or to solve the question number or the part number 2 of this question. Okay. So you need to draw or you need to understand how to draw this phasor diagram and what is the relation between V phase with internal voltage EA and with the armature current IA. Okay, so we already said before, the angle between the armature current and the phase voltage or terminal voltage, here we call it the theta. So this theta, its cosine represent the power factor. Okay, so you can see here theta equal to 36.87. This come from where? cosine inverse 0.8 lagging. Okay, cosine inverse 0.8 lagging, we got the angle is 38.87. Okay, if you make cosine inverse, so you got 36.87, and this is the angle between the armature current and the voltage, and it is lagging. That means the armature current is comes after the voltage. So the voltage come first, and this is lagging by 38. So it came after that lag. Okay, lag by 38.8 degree. Then the angle between the phase voltage and the induced voltage or internal voltage of the generator, we call it delta. And if we go back, if you go back to the second video, I think second or third video about the on the phasor diagram of the synchronous generator, you will find what's the difference between delta, gamma, and also theta. Okay, we said if you remember delta here, we mentioned it, we call it the torque angle, or it is the angle of the torque, or it is also the angle between the phase voltage and the armature or induced voltage. And we said that this delta usually between 15 to 20 degree, and the base value for delta is 90, and at that point the power will be the highest value of the power. Okay, so here we will learn how to find the values of EA from, we already have B phase here, which is 277. This value we only know now in the no load, in the case of no load, but we don't know this value for the case of full load. So in this question he talked about the full load situation. So the full load situation will be different from no load, because the full load, that means we have a value for IA. No load, that means IA equal to 0. So for the full load here, IA will equal to 60 ampere. So as you can see here, this is the value of the full load armature current, which is 60 ampere. So the value of IA is 60 ampere. Okay, so when we talk about the lagging, we said lagging, that means the current come behind the voltage. So and the angle between or the voltage angle is 0. So B phase is on the x-axis, so its angle is 0. This angle is come lagging by 36. That voltage is come leading by angle of delta. Okay, so this is the formula how to write the relation of the we call it the armature reaction voltage or armature reaction voltage drop, which is GXSIA. So we have XS equal to 1 ohm, already mentioned before. XS is 1 ohm, and since we have we want to talk about the, we need to consider the angle of 1 ohm. X here is XL, correct? XL usually equal to positive J, any number here can be here, in this case J1. If it is capacitive, it will be XC, and its value will be, for example, negative J1. Okay, so this is the difference. When we say J1, that means it is 1 with angle of 90 degree. When we say negative 1, this also equal to 1 with the angle of negative 90. So this one is 1, it's like 1, this J1 is like 1 with angle of 90 times 60 with angle of negative 36. So 90 minus 36.87, it will give you the value of 53.13. Okay, 60 times 1, it will be 60. So this will be the voltage drop or the armature reaction for the synchronous generator. In order to find the value of phase current with the full load with power factor 0.8 lagging, we need to use this equation. Actually, we already highlight this equation or use this equation in the previous videos. So you go back to the video of the phasor diagram, you will see this equation. So, or you just, if we go back here to the phasor diagram, if I ask you now how to find the value of EA here, so this is the triangular here. We have this triangular, this right angle triangle, correct? So the hypotenuse here, square of the hypotenuse equal to the square of the adjacent plus square of the opposite, correct? So this, the square of this line equal to the square of that line plus the square of that line. So this is Pythagoras law. So we just have EA square will equal to XSIA cosine theta square plus V phase, until here we call it V phase, correct? So this is V phase square plus XSIA sine square. This is actually this is V phase until this point, okay, until this point. Then we have here XSIA sine theta, okay. So this will be square, this will be square, this will be square, and the IA will be square, okay. So just by applying this Pythagoras law, so we can got this equation. Now we need to substitute for the value. We have EA for the no load already 277, okay. This we call it the internal voltage, and the internal voltage is fixed or constant for the generator, not change. The one that will be changed is the with the load is the value of V phase. In the case of no load, EA equal to V phase, but in the case of the load, V phase will be either lower or higher than EA. Okay, depends on the load power factor. Plus XSIA sin theta and XSAA cosine theta here or square. You substitute for the value of XS, which is 160, same sine the angle here, which is 36, has the same XSIA cosine the angle, which is 36. You solve the equation for V phase, you are going to find the value of V phase, which is 236. So V phase, if the power factor is lagging, V phase less than EA. This is because power factor lagging. Okay, so this is the first part in the section. I mean, in the part in the question, in the part B of the question here or of the example. So this V phase that we found, it is for phase. If we want to find for the terminal, we need to find. We said V phase equal to V terminal over Z3, or V terminal will equal to Z3 V phase. So here we apply this one. V Z3 V phase already there, which is 2369, 236.8. So we substitute here, we got the value is 480. So this will be the terminal that the generator will provide through its or this the terminal voltage of the synchronous generator will be 410 between phase to phase. I mean between or line to line, okay, but not the phase voltage. The phase voltage is 236.8. So again, we are going to redraw the phasor diagram for the case of power factor equal to 1. And if the power factor equal to 1, you can see here, this is IA, this IA here, it's there, this is the line of IA. It is in phase with the value of V phase. Okay, it is in phase with V phi here. So both in phase, that means the angle between them is equal to 0. No angle. If I have line, then I have line on it, same line. So what is the angle between these two lines? It is 0. So this 0, that means cosine 0 is equal to 1. So this is the case of power factor equal to 1. Okay, that means the angle between the current and voltage is equal to 0. No lagging, no leading, they are in phase. So in this case, power factor will equal to 1. So we need to find, or to complete the drawing here, which is EA, we need to draw the value of EA, which is the internal voltage of the generator. The value of EA is 277, no change because it's constant. And we have here the voltage drop across the armature windings, which is XSIA. So this we call it the synchronous reactance or armature reaction here. So it's voltage drop IA XS. XS is equal to 1. IA is equal to 60 for full load. So it will be like 1 or 60 with the angle of 90 here. So the same, we are going to apply the formula, apply Pythagoras law. So it will be EA square equal to XSIA square plus P phase square. Okay. So this is the formula here. EA square equal to V phase square plus XSIA square. So we substitute for EA by its value 277, V phase square, and XS here the value is 1, IA value is 60. You substitute, you solve for V phase, you find the value of V phase is equal to 270. Okay, so you can see here the value of V phase is 236 in the case of lagging. Here the value of V phase is a little bit or approximately near to the EA. because the power factor is equal to 1. So almost V phase equal to EA. EA is 277 and here V phase equal to 270. So almost the same, near to each other, because the power factor will not affect, or the unity power factor will not affect the voltage of the generator. This is the ideal case, that you have power factor equal to 1, or your load is resistive load or pure resistive load. Okay, so this is for the case of power factor equal to 1. Also, the third part will be for the case of power factor which is leading, and in this case we said if it's leading, the V phase will be greater than A. So the terminal voltage will be higher than the voltage generated by the generator. Why? From where the extra voltage we got? We got it from the capacitive load. Okay. So this is the case of the ladding. Actually, here also we need to multiply by Ch3 because we want to find the terminal. So it becomes 468. This is the third case for the leading power factor. So you can see here leading power factor. So in this case, the leading power factor, the value of V phase will be higher than the value of EA. EA is 277, but V phase must be higher than 277. Okay. Why? Because in this case, the current is leading, so it's come before the voltage. So you see the current is here and the voltage is lagging. So the current is leading. For that we said it is a leading power factor. It's leading by angle of theta, and theta here is the same 36.87. It is the same because you said 0.8. So 0.8 either lagging or leading, it equal to, when you make cosine inverse, it will give you 36.87, but in this case it will be positive because it's leading. So here this is the angle, and if we want to apply the Pythagoras law on this triangular or right triangular here, it will be the same, but we are going to consider this line and this line. So until this part here, it will not be V phase, it will be V phase minus this part, because V phase is longer, so it will be V phase minus XSIS and theta. For that, you can see here in the equation here, V phase minus XSIA square. Here, XSIA cosine theta square and EA square. Substitute for the values. Solve for V phase. You will get V phase equal to 308. So V phase in this case is greater than EA. That means the voltage that we are going to take from the generator will be higher than the generated voltage by the generator itself. The extra in the voltage here is come from the load or from the capacitive load. Capacitive load will give you the extra in the voltage, or will compensate or will boost your voltage of the generator. Okay, so in this case we are using we have the leading power factor, so we are going to solve. So the voltage terminals will be 535, which is also higher than the terminal voltage in the first case of the lagging and also of the unity power factor. So this how to investigate the different impact of the power factor on the voltage output or the output voltage of the generator, synchronous generator. Okay, so the next part will be the part C here. He asked about the output power of the generator at 60 ampere, zero point 0.8 power factor lagging. So since you have the formula of the power, set B equal to set 3, since we have 3 phase, so we set 3 V phase or V terminal IA cosine theta, or will be 3 V phase IA cosine theta. Either both will give you the same answer if you use set 3 VT or you use 3 V phase. So since we have the V phase already, just we use the V phase in this case, and V phase we are going to substitute for the lagging. He said the lagging, so the lagging, that means we are going to use the V phase for the lagging part, which is here 236. It's not for the unity power factor, or not for the leading, but for the lagging. If we are going to use the V terminal, we should use the 420. Okay, so here this is 236.8. The current, the full load is 60 ampere. The power factor is 0.8. So the total power or the output power here will be 34.1. This is the output power. if he asks about the input power, so the input power will equal to the output power plus the losses. So we have the losses from frictional loss and core loss and mechanical loss also. So all these losses will be added to the P out in order to give you the input power. So we have the P out, which is 34.1, the one that we got here. You just substitute here. Then we have the losses for I square R already ignored. He said equal to 0, so it's ignored, so 0. Then we have the losses for the core loss, the losses for the mechanical loss. The total will be 36.6 kilowatt. Okay, so this will be the P in and this will be the P out. In order to find the efficiency, we need to divide P out over P in, so you will get the efficiency of the generator. So the efficiency of generator here will be 341 over 36.6 times 100, so it will be, the efficiency is 93.2. Okay, then the last part here, to find that, I mean the next part will be to find the torque. So we know the formula for the torque, tau, sorry, the formula for the torque, tau, equal to P over omega. Whatever is the tau applied, induced, and so on, we are going to change the P out. Is it P out, P induced, P converted, and so on? And omega, is it omega M or omega S? But here we only have omega M, so it is the same, just substitute. So the applied torque here is represent the input torque from the prime mover to the generator. Okay, so it is the input torque from the prime mover is the generator, so it can be calculated by considering the P in value. So the P in here is 36.6 and the omega M is 125.7. we already calculated before, so it gives you the applied torque or the input torque of the generator. This torque will be converted into electrical power later on. Okay, when we talk about the induced torque here, so the induced torque, we need to consider only the P converted, not the P input. In this case, we consider the P input when we calculate the applied torque, but when we want to, the induced torque, that means the torque which converted from the rotor to the stator windings, or from mechanical to electrical power, so we need to consider only the P converted. So the P converted here over omega M, and in our case, the P converted equal to P out. Why? Because we do not have any losses in the, we ignore the losses in the armature windings, and we said IA square R is ignored, so the converted power is the same as the P out power, so we just substitute for the P out over the omega M, so you got the value of the induced torque. Okay, the last part is the calculation of the voltage regulation here. So in order, we said since the power factor will affect the performance or the output voltage of the generator, so we need to use some performance matrix to measure or to indicate how this generator is behaved. So the voltage regulation here is a relation between the voltage at no load, the voltage at full load over the voltage at full load. So at no load is 480 for all case, 480, 480. Okay, so this is the voltage at no load. That means no load means IA equal to 0. Okay, at full load means IA equal to 60 ampere. So this is the voltage at full load for power factor lagging, which is 480. When power factor, this actually we got it 410 is from here. You can see this one. This is the 410 is the, for the power factor is lagging. The V full load is 410. For the power factor equal to 1, the V full load is 468.4. For the power factor equal to 0.8 leading, the voltage will be 535. Okay, so these are the three values that we are going to substitute to find the voltage regulation for the three cases. So 410, 468, 535, and the denominator represent the full load here, so it is the same 410, 410, 468, 468, 535, 535. Okay, so you can see here, if the voltage regulator, if the voltage regulation of the synchronous generator is positive and is high value, so this is not good. Okay, if it is negative, or in this case it means we have lagging power factor, and also the voltage on the terminal of the generator is much less than the voltage on the generated by the generator at no load. Okay, so here the same, if it's almost near to, I mean the ideal value is 0. That means 0 means, if we set 0, that means the V full load equal to the V no load. Okay, so if this formula applicable, so we are going to find the voltage regulator equal to 0, and this is a good case or ideal case. If you have negative, it's also good, and the voltage that you will take from the output of the generator will be higher than the induced voltage in the generator itself. Okay, so this the two example of chapter 6, and hopefully it's clear. So try to apply or try to resolve this example again. Thank you.